let's do our usual review of what we covered last time. So I see Wasi absent, I see AJ absent, I see Ethan Jackson absent. All right, I want to be fair. I mostly started maybe down here. Last time I started doing from up there so that I give people a chance. Maybe you're at a higher level, Nathan. I'll start with you. Nathan, define a beam geometry. That's it. That's it. The cross section, I did not mention it. As long as it's in one dimension, we call it a beam. The cross section could be anything. It could be uniform or even non-uniform. Nathan Schaffner point. All right, and let me go to Sander. Sander, we looked at two geometry loading cases. One was cantilever, the other one was simply supported beam. And actually you and Jansen, you give me please the max deformation or deflection equation for cantilever, and Jansen, you please give me the one for simply supported beam.
So for the max equation?
Yes, max deflection.
5.
No, you give me for cantilever. Jansen should give me the one that you were about to mention. Please prepare.
It's FL to the third, and then 3 over 3.
Over 3. All right, go for it.
5 WL to the fourth over 384 EI.
Good. All right, so really in that topic, it was really as big as this, just these two max deflection equations. Make sure you do not forget them, because we had some students previously that they forgot. They had no idea what the equations were. All right, so this one, Jack, I make it open to everybody and I get back to you. So stress transformation. What do we mean by stress transformation? Where or when would you apply that? So conceptually, there was something mentioned about that. So where or when would you do stress transformation? All right, step back, one more question. What kind of quantity is stress? Actually, it goes to Jack. What kind of stress, what kind of quantity is it? Speaking of scalars, vectors, there was one more we talked about last time.
It's tensile.
You can overhear it properly. Something else. All right, open question. What is it?
Tensors.
Tensor, we pronounce it. Tensor. French would say that way, tensor, like that.
E-N-S-O-R.
Yes. I want to put present for Ethan. I just need a little bit of time. Where is Ethan? All right, yes, gave tensor. So speaking of tensors, we said stresses are second order tensors, which could be presented or formatted in a matrix form. 3 by 3, And speaking of stress transformation that I just asked about, basically we said if we look at the garment as an application, we load it in X, Y, or we cause shear, what happens to particular fiber? The fiber in a particular orientation. We know what we loaded. Guys, you open up your laptop and you're not paying attention. You're loading the garment, X in X, Y, and then with shear, what happens to particular fiber, and then angle. That's why you would need to do stress transformation. All right, so speaking of that, Ethan, I know that you just showed up. If you're ready, go for it, but if not, I want to ask these three big equations that we have. The next three, prepare for those. Sigma x prime, sigma y prime, tau x prime, y prime. One of you, please give me one. Gray and then Audrey, depending on whether Ethan is prepared. If not, then Leo will give you please the third one.
You want the,
Sigma x prime equation.
I think I have it. Is it?
Say it is. Believe in yourself. You're looking at your own handwriting.
It is sigma x equals sigma average plus sigma x minus sigma y over 2 cosine 2 theta plus tau xy sine 2 theta.
Guess what? If you were asking, and then if I said yes, then you would have to repeat all of that. But you said it is, that's correct. All right, go for, Greg, go for the next one, please. Sigma y prime.
Sigma y prime would be equal to sigma average minus sigma x minus sigma y over 2 cos 20 minus tau subscript xy.
Where are you getting that? Where are you getting that?
Where am I getting this?
Yeah, that angle, it's not like that. 2 times theta.
2 times theta.
Yeah, cosine 2 theta, that's it. And then continue minus tau xy. It's okay, look at that, but make sure you get a copy of that. Transfer it to your notes.
Yeah, I incorrectly transferred mine. Yeah, and then there's constant theta. That was the end of it.
There was one more term. Minus tau.
Oh yeah, minus tau xy sine 2 theta.
Sine 2 theta. Make sure you do have it correctly.
Yeah.
All right, point to you. Audrey, please go for the last one. Tau x prime, y prime.
Tau x y prime equals minus sigma x minus sigma y over 2 sine 2 theta plus tau x y cosine 2 theta.
Very good. Point two. Again, on the fiber, what's the stress that is observing? These are the three that's observing. Even though we load them with x, y, and tau. So that's why you call them the prime values. All right, point to you. Leo, when we say planar stress or plane stress, what do we mean by that? If you go with the common sense, planar, plane on the plane, gives you some hint. Everything is in one plane, but what happens to the stress tensor or the matrix in this case?
On the face.
So a 3 by 3 matrix, how many elements does it have?
6.
3 by 3. Yeah, but overall, how many elements does it have? 3 by 3. How many elements? 9. All right. You said 6 because 6 of them are independent. That's correct. So speaking of that, if I say this tensor is planar, what happens to this? We know something about some of the elements then. That's okay. Anybody remembers that? Leon? I'm sorry, Drew?
That there would be no forces acting in the Z direction. Or in the current way.
Almost there, but let me see what Olivia wanted to say.
I was just gonna say there's no dependence on Z, so they go to zero.
That's a better way of saying that. I'll give you a point, Drew, this time. Leon, so when you say planar, that means everything is on one plane, no dependence on Z. So not force, no dependence on Z. The force could be there, but it will not affect what happens in Z. Okay, true? All right, so we had that. So basically the third row, the third column, all those 5 elements would be zeros for planar stress case. All right, we had that, and then I moved to packs. Packs, speaking of Moore's circle, the center of the circle, what symbol did we give it to?
Sigma average.
Sigma average. And then the radius of the Moore circle gave, what parameter did we assign it?
The radius would be sigma max.
Something else. Pay more attention.
Plus
Pay more attention.
tau max.
Tau max. All right, the center is sigma average, and the radius is tau max. Then, Reagan, please give us the equation for tau max.
Tau max is sigma average plus radius,
Tau max.
plus tau max.
Tau max.
Tau max?
That's sigma max.
Tau max is the, what's that?
Sigma. Square root?
Yeah, square root.
Square root.
Sigma x minus sigma y over 2 squared plus tau max. Or plus tau xy.
Also tau is,
Also tau squared?
yes. So it's good that we're reviewing that. Reagan, I sympathize with you. That square root, it's not in square, is it? All right, point to you. Yes, square root of sigma x minus sigma y, all over 2 squared plus tau xy squared. That's tau max. Olivia, please give us sigma max and sigma min equations. Okay, they're really similar.
Sigma max would be sigma average plus r, and then sigma min would be sigma average minus r.
And the equation for sigma average,
Sigma average is sigma x minus sigma, or plus sigma y over 2.
yes, that's what we call it average, right? All right, I point to you. Tyler, the combination of sigma max and sigma min, you had the terminology, we call them something.
Principal stresses?
Principal stresses. Basically, loosely extreme stresses. All right, and then Evan, please give me the angle that represents the principal stress, or basically give me the principal angle.
Theta subscript p equals 1/2 inverse tangent of 2 times tau xy over sigma x minus sigma y.
Correct. All right, we have that. All right, let's see what else I can. All right, let's do this practice. Okay, it's Drew. Drew, picture the Moore circle. We know that every point has 2 coordinates, right? On the plane x, y values, right? 2 coordinates, 2 values. All right. So, but there the coordinates are sigma and tau. Sigma is horizontally to the right, tau is vertically downward. Picture that. All right. Give me the locations of sigma max, sigma min, and tau max.
tau values, they would be located at sigma average, and then the height of, and then located at, in terms of, and tau coordinates being tau max and tau min. And then just,
So you said below sigma max, you said there is tau max. You said the bottommost is tau max. That's correct? Give me the location of sigma max.
sigma max would be located, is located at, at voltage, it's,
At where?
sorry, it's, that would be located at, it would be located at tau average,
So speaking of the circle, so maybe I can draw one here. Just make it easy. So you said, right, this is sigma average. Right below you said this is tau max. Good. So where is sigma max on this?
to the right,
Okay, good. Sigma max. And the sigma min?
to the left.
To the left. All right, good.
Sorry.
All right, point to you. And then call, look at these points. Look at sigma max in particular. Give me please the coordinates of that point. You know that every point has two coordinates, sigma and tau value. So this is sigma, this is tau. Give me please the coordinates of sigma max. The sigma is the sigma of that point, we call it what?
I'm gonna pass for today. I'm a little out of it.
No worries, no worries.
What was the question?
No, the next one. Yeah,
Sorry.
no, the Aiden, it might apply to you as well, your review, so it's fine. I want to ask now, Josiah, that every point here has coordinates, right? X, Y coordinates. X in this case is sigma, Y is tau downward, all right? So give me the coordinates of this point. The coordinates of this. Maybe you guys are misunderstanding my question. Maybe you might give more explanation. This is point A. Suppose this is 5. Suppose this is 4. Josiah, what are the coordinates of point A in this order, X and Y?
5, 4.
5, 4. Suppose this is X and I define Y to be like this. Downward is positive. What are the coordinates of A? 5 and -4. Do the same thing. This is sigma, this is tau. What are the coordinates of sigma max? How far should you go to the right on the sigma axis? I gave you the label. How much?
Sigma average.
This point, sigma average is here. This point is however much sigma max is. Go sigma max to the right. All right?
Sigma max.
And then how much should you go up or down?
You don't go up and down.
How much?
0.
0. The coordinates are?
Sigma max, 0.
You said it. Now go for tau max.
Tau max would be tau max, 0. Or no, it goes down, so it would be negative tau max.
Downward is positive, isn't it?
It's positive tau max.
That's the tau value. That's good, but what's the sigma of it again?
Sigma 0, because it doesn't move like
Look at, you see, from here to here, you gave me the x coordinate. From here to here,
Oh, sigma min. Or sigma average.
sigma average. Do the same thing for sigma min now.
Sigma min is negative sigma min.
Why is it call it negative? What the value is?
Just sigma min.
Sigma min. If it's negative, it is negative. sigma min, and the y coordinate?
0.
0. All right. So basically, here, the principal state, tau equals 0 on it. And on this one, tau is max, but sigma is sigma average. So what does that mean? The material, the fiber on the material that is observing max, normal, and minimum stresses never sees any shear. But the one that sees max shear stresses sees certain normal stress on it. So if the material has to fail, guys, please pay attention. Pay attention. If the material has to fail, it fails either on this or on this. On more circle, this is 90 degrees. But we talked about it because we had twice stated the equation. Really, in practice, it's in 45 degrees. So if you have an object, you want to physically or geometrically see which faces are being failed, we got two perpendicular faces. If either this or 45 degrees, these two are critical faces. So that's why in bridge case, we looked at the mid face and only one of the extreme faces, up or down. Only one of those could fail. Those are the two cases that we have to consider. Again, the terminology here replicates that behavior. All right, just sorry before I forget, let's give you a point. All right, what else can I ask? All right, Nathan, in the previous example that we did, we calculated theta P. We said that's the critical fiber angle, right? And then, remember how we came up with whether this is 52 or this one? Whether it's this one that I have to put 52, we said one of them is sigma max, one of them is sigma min that we already calculated, right? But you remember how we figured out that this is 52, not that one? Anybody remembers that?
Didn't we solve that in the previous problem? We got 52 from a.
Yeah, Jesus, I'm asking, you found 52 and 84 from here, yes.
Yeah,
But
we
when-
found.
Which one is 52 that I have to put here? Why did I put 52 on this? Why not on this?
Because that's sigma
That's
max.
my question.
Sigma
Yeah, but
max.
sigma max could occur on this or this.
It's because it's in an X direction, I guess.
There was a way that I
I know. but I-
went over. Anybody remembers that? Yes.
Is it because the 84 was negative and the two y-axis ones are pushing in?
That wasn't the reason.
I didn't get that reason.
So we said, simply do this. There are two ways. One way, we're going to do actually both in the next example. But the one that we did was this, Jesus. We said, always start from X and see whether it rotates easily to sigma max or all the way to sigma min. And I still have that arrow. Is it easier to here or here? Because
That's
it's
what you
easier to get to sigma max, the one, I have to put sigma max on this
52.
way.
Since it was okay, I got it. It rotated easy to 52, and that's why it's.
That's
there.
why you put 52.
Okay.
Yeah. And then the next example, I planned it so that the
Right.
other one happens. We're gonna practice it. So Justin, next is yours, this one is yours. We're just practicing that computation again on a new element. So let's do that.
I don't know how to write that. How would I write this?
Remember, the max shear stress is basically tau max you're after. The normal stress corresponding to that, Josiah just confirmed this for us. This is sigma average. Principal stresses, Tyler said it, as sigma max and sigma min. All right, Justin, we said we want to draw the circle, extract the x, y coordinates, sigma x, tau x, y, sigma y, tau y x. This one in particular, we know that's always equal and opposite, so we don't have to calculate this. So we need 3 dependent values. Look at the diagram and then emphasize the signs, please.
Sigma x is 50.
Yeah.
Negative 50.
Emphasize the sign.
Positive 58 megapascals. Sigma y is 100 megapascals. Positive 100 megapascals. And then tau xy is 40, positive 40 megapascals.
Remind us how you determine the sign of this.
The 100 megapascals is pushing down, which is a tension, positive in my mind. And then sigma
For
x.
tau, I meant.
Oh, for tau. I'm gonna be honest, I just gotta guess on that.
That's okay. This one, always look at this one.
That's it.
Upward, positive, downward, negative. Or the proper is the one that you were about to mention. Look at the center. Does this one create counterclockwise or clockwise?
Counterclockwise.
That's positive. Or should we look at this, upward, positive, downward, negative? Okay. All right, we have these values. Let's draw the circle. Sigma, tau, because we're working all in mega, simply put the unit by the label so that we do not keep repeating those units. All right, Jacob, please help me as a GPS. I'm at the center. Get me to point X. Jacob, as a GPS, this is to the right positive, downward positive.
So to the right 50.
All right, somewhere here.
X.
It has 2 coordinates. Get me to point X.
To the right 50.
Yes?
Down 40.
Downward. So that's X, all right. I'm back at origin for Y.
And then to the right 100 and up 40.
All right, very good. All right, now you want to draw the circle connected to this point. Kiro is called what?
Tau average. Wait.
Kiro, just look at the axes, the 2 axes. It's on which axis?
The x-axis or the stress axis?
Yeah, but what, yes. Isn't it this? What average now?
Stress, sigma average.
Sigma average, not tau average. Sigma average. Give me the equation for that, please.
Is sigma x plus sigma y divided by 2.
All right, we have 50 plus 100. So So 75 megapascal, we have the value. So draw a circle with sigma average as the center of the circle, but it should pass through x and y. So do your best, something like this. We just did that. You said sigma max is on the far right, sigma min is the far left. Right below sigma average is tau max. Zero point. So we just did the circle. Now let's calculate those values. Max shear stress, we just reviewed that, but Braden, please give me the equation for tau max, which we said is also the radius.
Got that right. That is the square root of the, sigma average, wait, no, it's not sigma average, it's sigma x minus sigma y over 2 squared.
And Braden, believe it or not, people have been making that mistake. I'm glad.
Well,
you
I
fixed
thought it would, yeah, it's subtracted though, so.
Yeah,
But-
because it's negative, there's not.
Yeah.
All right, yes, please continue now.
And then still under that square root, you add the tau x y squared.
That's correct. And that you said still under the square root. We had one student right in the previous section that put it outside. All right, good. So we have the value here. All right, get your hands dirty. Calculate it, give it to me, and I'll give you a point. All right, okay. Gabe, what's the value you found?
47.17.
Sounds about right. Yes, all right, then confirm it. Gave the point. 47.17 megapascal. Olivia. Justin, Drew, Audrey, Leo, Jansen, Reagan, Jacob, Cole, Rosario, Evan, Hero, Pax, Nathan, Jack, Gray, Tyler, Sturdy, Ethan, Jesus, Aidan, Nathan, and Braden.
Not actually confirming.
You're asking a question.
Yeah, for whatever reason, he's getting 85 back, and I have exactly.
Are you putting 40 inside and then you squaring that out? Bring up your calculator, let me see. Oh, you put a plus sign and see it's negative. With this one. fix that, I already gave you the point. Do that. All right, so we have tau max. All right, corresponding normal stress, sigma average, we already did that, sigma max, sigma min. Jesus, give me the equation for sigma max and sigma min, please.
Sigma average plus R for max, and sigma min is sigma average minus R.
That's good. All right, this one is straightforward. So 75 plus 47.17, and this one quotes basically means the same values, only the sign is changing in between. So 122.17 megapascal, 27.83 megapascal. Nathan, did you confirm?
Okay.
Okay. All right, Jesus at point. Yes, great.
I just have a quick question. For the sigma max and sigma min, why do we declare tau max as R? Is there a reason?
Because, yeah, by inspection, you see that the tau max starts from 0 all the way to tau max value, right? Isn't it the radius of the circle?
Okay, yep. That makes sense.
All right, before we do the last part, let's do suppose question here. Switch to blue. Suppose sigma ut is under 50, sigma uc is 10 megapascal, tau u is 50 megapascal. All right, we have 3 people left, starting from Dylan. Once you're ready, I want you each to tell me, based on one of the criteria here, whether, based on our calculations, the system is safe and why. So Dylan, based on this alone, would you say it's safe and why?
Yeah.
So what's your reasoning? You compared what with what?
The 50 and the 100.
Which one, which one?
Both intentions.
Oh, these are inputs, right? These are the load that we're putting in the system.
Yeah.
But the system says there is a fiber that is observing this much. Would you fall for 50 or 100? Or sigma max?
I see.
Always look at sigma max, sigma min, and tau max.
All right.
Then correct it. Or update your answer.
Yeah, then yeah, I'd say if they're all below 150.
Just based on this alone. Just based on this alone. Let's do one at a time.
I'm talking about that one, yeah.
Yeah, or
It's
which number are you comparing this with?
the 122.
All right, this is greater than 122, so it is safe. That's good. All right, next one. Sigma UC is 30. It is safe. And what's your reasoning? Which number are you comparing with? Is it safe?
Oh, sorry, no, that's not it.
Is down here. Take it again.
It's 27.3.
Take it again. Sigma UC, what does that mean? Compression. Do we have any compression there? Sigma min, is it negative?
Oh, no, it's not.
What's the sigma, basically the max compression that you could see there? None. So it is safe or not? Safe. So this is greater than 0, so it is safe. So I'll look at the max positive, the max negative. All right, last one, Adam, please.
Is it safe because it's greater than sigma min?
Greater than what?
The sigma minimum.
You see, this is tau u, right? Tau u. You have to compare it to tau max.
Because it's greater
So is it safe or not?
No.
50 is not greater than 40. U means ultimate, means strength. It can take up to that much. This tells me I can handle up to 50. You're giving it 47. Is it good or not?
Oh, that was the other way around. Yeah, it's safe.
It is safe. All right. Adam, please write it down somewhere. U means ultimate, means the strength, the max value the material can handle. All right, I point to you. So that was the supposed question. Now we want to do the last one. Draw the principal state with reference to initial state. Remember that on the Moore circle, this is the principal state. And this one is the initial state. And the angle between the two is twice theta p. And the Morse are called twice because all the equations that we have there, sine and cosine, if you recall, the big equations have twice as part of the angle. But in the physical sense, we want to draw that in the physical sense. So we do that in here. So this means I have to calculate theta p. So let's reverse the direction from you, Aidan. Aidan, please give me the equation for theta p.
One half inverse tangent, and then 2 tau xy over sigma x minus sigma y.
All right, very good. All right, this gives you minus 29 degrees. So if this is our x, minus means counterclockwise. So you go counterclockwise. Separate the 29 degrees. Put the square or element in that orientation. On this, we said there's no tau. Tau equals 0. That's principal state. This is initial state. This is principal state. So all I need are these two pairs. One is sigma max, the other one is sigma min. No tangential. Why? Josiah said to us today that sigma max and sigma min both have 0 shear stress coordinates. So no tangential stress on that. All right, sturdy. We had, let me see, Aidan. Aidan, I will give you a point for that before I forget. All right, sturdy. Now this one, you want to decide whether, we know that one pair is sigma max, the other one is sigma min. Jesus, this is the question that you had. I confirmed with you. So sigma max, sigma min. So this one, is this sigma max or sigma min?
Sigma max.
And what was your reasoning?
It's closer to that. It's easier to use it.
Easier from which point? Is it always start from which point?
The initial state.
From which point on the initial state? That's 2 points. The two ends, look at that. Which point we start from? Look at the previous one. Did we start from Y point there? I emphasize that. Sturdy. The previous example, you have it there, right?
Yeah.
So, see, you got sigma max, right? If we start from Y there, will you get sigma max?
Those are math.
What with this one? We didn't start from Y there. You confirm AJ is absent. And Nick is of course excused. All right, thirdly, here, the previous one that we did. So here, you see I circled it. All the stuff from X. From X. And see which,
I said that the second
oh, you said that, I'm
Yeah.
sorry.
Oh,
Okay. Start from X and then which one would you get?
Sigma then.
Sigma min then. See that? All this stuff from X, it's easy to get to sigma min. So you have to put sigma min on this. Because it's already positive, you just put outward, put 27.83 on that, and the other one has to be sigma max, which is 120,217. It's 30 point. So really, this means all the fibers in these directions will translate to these are the critical stresses, critical fibers. They start to get damaged. So now we want to do the books approach, and I want everybody to do that and get the point. I want you guys now this time, bring your work to me and let me confirm. So basically the book is saying this. What is this value? It says do this. In sigma x prime equation, put theta to be theta p, and you should get 27.83 megapascal. So show me the work, do the big formula for sigma x prime, put the sigma x, sigma y, tau x, y values in there. For theta, put theta p, which is negative 29 degrees. Make sure in your calculator you have it in the right setting. So do that and then bring it to me here. Let me confirm and give you a point. What would you have tangent there? That's the big equation for sigma x prime. We use that for that. That's 27. That's 27. This is radius, but this is.
Bless you.
Oh, this is tau x, tau x, y times y. Just replace that value right now. I believe that was 40. Yeah, Please do that so that we resolve all those small issues that could arise in test. Thirdly, I see you look quizzical. This big equation you have for sigma x prime, use that, put all the sigma x, sigma y times y values in it. For theta, put theta p. That's good.
Oh, I see what you're talking about. I like.
It's showing how it's just the individual. It's the problem you're solving for. It's a negative sigma prime. You're showing that both doesn't sigma prime. You're showing the answer. Yeah.
The value would change.
We need to solve that. Yeah, that's the only way to solve it.
What you have two different signs here. Well, you have,
This is
oh, that's the reason. If you do that, you did the other one. See that? So the text says the one that you did, just do all this work to get that. We did calculate it. We were just practicing. You don't have to do all, guys, you don't have to do sigma y prime, tau x prime, y prime. I asked you, this is the first one.
I did that.
Oh, all right, just because he did both of them. We did three.
Yeah, I
All right, this is the one.
90 degrees.
Yeah.
Because it's negative, angle is negative.
So,
Where is negative sign? Why don't we do that? We did this should be negative, this should be negative.
I think this is.
But look at this.
But I got the right answer.
Just
yeah.
that one.
He said
It should have one or two. I don't know how you.
Oh, yeah, this is.
Yeah, so much you could quit. That's the beginning.
Yeah, I figured that's good.
That's good.
I looked at the corner, there's no way, right? When that is consideration, it says rad, I'm like, all right, well, actually.
Scott is a.
Right.
And all very engineers, right? All the
Yeah.
yeah, it's important, right? And when the testing game is this way, you fix it.
Oh, fine. I don't know.
Is that 29?
That is a team. This is probably easier.
That's how you do it.
You fix that? Yeah, you see. You know what? No. Really. undergraduate, you're always smiling. That's great. Okay, let me see. I want to make sure that you keep smiling after this. That's good. That's good. That's good. Office unit. See, all right.
This one is so much more.
All right.
Why do you feel like my name is Kevin?
It's in the class. Yeah, like that.
What's in the document on that? I sure it looks
That's what you got now, right?
We don't. Okay, I looked at our scholarship here and just go, I cheated in US.
Maybe the science, you're not.
Mine's an HVAC.
You fix this here.
He was like, how'd you do on your test? I was like, I got 100%. He's like, that's an odd thing that you were crashing out right before. And then he's like, I'm like, are you accusing me of cheating? He's like, yes. I go, I cheated. That was my
This is what I was saying, but I didn't know that we had to take this. When you do that, then this gets. That's what I do is
So I was
unit there, megapascal.
Oh, like the
Rated,
Take a look at the chart.
Boy, not single maximum. Big equations. Big equations, they never have single maximum. Single max, single boy, how? But why did you use single max and single min? Yeah, single x doesn't say single max. Single x, that's single y. Yes. If you had those, what would you care about all those guys?
because we're just doing it all.
Yeah.
Let's get it, put a dog out.
Yeah.
So you would never.
Engineer, right? What's the unit, right? Oh, yeah. Well,
I'm working on it. Not quite, at least I got 40 hours.
At least work on that. This is.
Like, is there
I see. Because term by term, it changes, right? When we get to the end of the term, let's see who got the max and then say, okay.
no more after that?
No, basically, using the cap, so you're gonna get this 5%, right? Right? So if you bring the cap lower, a lot of them will get 5%. So I do that with you. I want to see how many people, what is the basically spectrum? Look at that, and say, okay, let's put the cap here, so that more people get the fund.
This is like the
Don't worry about we need that, one that you did us.
although you had just go up to your cursor.
What do you get? Isn't it
No. When it does, when it did work. The laser thing is bad. It's bad. You get all the drivers. Later by like this.
These are small issues. This is the same. So you have to put theta to be the same value of theta here. Okay, redo that.
Oh, wait, never mind.
Huh?
Right, so.
Yeah, I didn't know KDP means using the Saxon numbers. I guess so.
Okay, so. I mean, this one's it is literally the same.
Take a picture of this.
One more than one.
Why specifically?
Well,
Yeah.
that should be degree.
Okay, that's what I mean.
But yes.
Did I try to close in negative 58? It gives me positive 5.299. You're supposed to get that? Yeah. Okay.
Is this super cap?
Oh yeah, yeah, but that's negative too. Negative.
Is it a 2 or 3 or? Yeah.
Will be, yeah, will be negative.
I mean,
So is that
It'll be like negative 30.
Oh shit, he's got super cap.
He's at super.
yeah, negative 14.2749. Okay.
But get the chance from your class.
That's 71.
We'll figure it out.
41. 47. 17.
Why?
Yeah.
Specifically.
Oh wait, fuck, I realized. It's supposed to be 40, right? Yeah.
That thing's ugly as fuck.
Maybe.
The Ram logo looks completely out of place. The Ram logo looks completely out of place. I get it, but it's I expect that to be on a truck.
Negative 19.
Let's use Mac.
Yes.
You say Raven Guard? You say Raven Guard? Raven Guard? Okay, never mind. Don't worry about it.
No, we're talking about a Dodge Charger.
Okay, I thought you were talking about like Warhammer.
No,
Yeah,
no,
okay.
no, we're not talking about
All right, all right.
Let's just use a. It would figure out how to. I'm pretty sure that is like the one with the capacity to 1,000%. Before the back, I've never actually like, never. I thought the Challenger was way better.
Yes, sir. Alright, then fix it right now.
I'm not a big Dodge fan anyways. Well, the Viper's pretty bad.
Until the 2015
It's so, the Viper is just oozes sex.
Yeah, that's also like 150 grand, but.
Yeah, but it's like, D10 makes it.
How do you get 122?
Like literally anything else.
I don't know. I put 29.
It should be 29.
Guys, well done. So if you had small calculation issue, we were able to fix it together. That's really the idea. It takes a little bit effort on both sides, me and you guys, but you should feel comfortable with that when it comes to the test. Make sure you have the right equation. Some of you did not. So fix it. Make sure you look at the notes properly, check it with your classmates, so that you have the right equation for the test. All right, what was the lesson here? The textbook says, guys, the textbook says, if you want to come up, what value you have to put in here, you have to do this equation. I said, no, you don't have to. Much easier. Just look at this x. Whichever is closer to, whether sigma min or sigma max. If it's closer to sigma min, with sigma min on that side. As easy as that. You already did the work for that. So that's really, whether this or that, it doesn't matter in the test, either one works. All right, guys, any questions? All right, let's get the break now, please. Come back by 11:32, and you're welcome to come here and pick up your test.
You're welcome to.
As in alphabetic order, please do not mess it up. Oh.
How did you do on the first? Yeah.
I got a 41.
Did you just 72?
That's fucking nice.
It's way better than I did.
100%. What's your grade right now?
I haven't checked the overall grade. Hopefully it's good.
Hopefully. I think you're good on
I'm worried about L3 a little bit. A lot of I'm gonna wait 10 voice chapters.
Can I still get a point?
Let's see what I bought over here. Actually, I'll let you hear it.
Yeah, this is like.
What? Can you raise this? You fixed it. So the rest is this. Make sure you read this.
Well, I wanted to see it.
Some.
Just I want to see builders.
So that equation we had on the page. And then through that we came to this one. Yeah. Already gave it.
Please,
That's what you read.
first. Oh, I thought he gave that to me. I was gonna be like, whoa, that's crazy.
I got two.
You did, okay.
Yeah, I didn't have to earlier. So you can see where I just went, well, fuck it. I guess it's a
It's pretty useful.
So I got 30, I got 47, 45. 49. He did hit me with the no.
No, yours is here because of what?
I'm sorry. So, I solved it. I solved the 34, so it should be zero automatically. As soon as I knew it was
Yeah, no, I put 0 and then I wrote down like if you could solve it, it's this.
oh, it's just so just in case.
Yeah, I realized after the fact, I was just like, we have a moment to see this could be 0. How is 0? But yeah, it said everything was done.
They graded the board on Saturday.
But
But when I went to put it there,
I just had it wrong.
okay, thank you.
So like I missed a sign, I don't think I did a conversion. So my answer came out as being safe, and I needed it safe. If you did it right, you were unsafe.
What'd you buy?
Oh,
What'd you buy? You said you bought
Oh.
something? Yeah.
so if I would have the right proceeding, I think I solved for the alternate wrong. The alternate was wrong.
Was it?
Yeah,
So I do like these shooting competitions. So I'm on this who's on sale. It's like it's
That's what I thought. I was like, technically, I'm going to
CPL, but
Yeah,
I
I put
usually
true
do
very
it.
slightly weaker. So it's good. Did he give you a check mark?
Wait, no, it is true. I never froze. I was like, I didn't know.
Wait. Oh, you flipped your true false. That's weird.
What?
No, yeah.
It's like, here's your true false. I was on the bottom of it.
No, technically it's false, but it's true. It's
Essentially the same thing. False.
Dude, there's your unit bending. Yeah. Anyways, I saw for R. I just went, no, it wasn't my grade. It might have. If you copy the outline, then it's on my equation sheet. Oh, no.
I put I is equal to 1 half of your base times height.
Yeah.
Cube.
I saw instead of.
I had no.
Oh, well, you have it. You have it.
Oh, I see what I
Because
did.
of the one. Anyways, sorry, one of the row.
No, because I didn't read the question. It says do in terms of A and B. I did it right, but I didn't do.
I knew it was
right.
wrong. I knew it was wrong.
B
I was
and
like, maybe I'll get some.
Because I thought we were doing it for a pound. But I forgot about it. B was G, and B was J. I didn't know how to do this.
The neutral axis exhibits no shear stress due to fear.
It's funny. I should have put B because I knew it was B. I don't know why I didn't put B.
Probably right after this is what we were talking about. It's like a competition.
Oh, wait, that's a true false.
But I was using this old one. That was I got that really excited.
Oh, that sucks. I knew the equation was good.
I know this one for next like that one. Shit,
Yeah, I'm not confusing.
Yeah.
I don't know why I put sigma. I put sigma is equal to FLCI plus or minus. Oh, I didn't know how to do it like that.
Yeah, you can see me solve.
Only one of them.
As soon as I handed it to him, I was like, shit. That was on the outside face, wasn't it?
Only one is apply. M is moment is only Y. Oh, I forgot.
Instead of
Okay, well, that's a little bit better.
oh, I didn't get yeah, good calculate.
Did I tell? I messed up. I didn't even
I saw first and then went, as soon as I handed it. Literally, as soon as I handed it, I was on the outside face.
I feel like I could have got more points. Not on the back end, for the front side. The front side was some of these. The numbers, the baby, the letters.
Well, these ones, I think honestly, what I was doing by equation sheet.
I saw
This stuff's all her stuff. And this stuff is the last.
Yeah, a lot of the stuff that's on here. Like the last section, so
Reasoning for.
deformation. That was
All right, guys, let's get back to this. We want to finish up the remaining slides between this and the next session. So the more we do today, the less we have to do next time. Yeah, that's the idea. Goal. We really like me and this class. We want to finish up. All right, so let's do this one. So yes, the test 2 results are posted on Blackboard with the statistics on the announcement page. As expected, the average was better than before. Again, we had a complete score. And please take advantage of the comments that I give there. Pay attention because this course is a core course and you're going to see this in future courses, at least in machine design. So please take advantage of those comments that I gave you. All right, with that said, now we want to do the problem from the very scratch. I mean, so far, every time we had the initial state given to us, all the stresses were there, we were able to do all the calculations. But today, from this point on, we want to actually do the practical problem. We want to come up with the element with the stresses on it, and then see really whether it's safe or not. All right, so this is really a practical problem. You have two pieces of wood, you glue them together, you pull on them, and you want to see whether the glue is safe or not. So how would you do that? So let's do that together. I'll give you time to write this down. And now I'm not sure who was the last person responded. I remember Sturdy now that gave me the angle. Maybe Dylan, you did not do the reverse direction. So Dylan, I think it's your turn.
All right.
All right, we have not done anything like this before, so let me give you the steps. So define the coordinate system. So we said planar. We're dealing with planar stress. So pick Z in zero state. So that means we know that when the force is applied, we do have stress in that direction. So pick that as X. We know that when we pull, nothing really happens laterally in this direction. So pick that as Z. This has to be 1. So pick X, Y, Z like that. Can add one more here. Pick X. along course. So put square or element on the x, y side of the object. So x, y side of that is somewhere in here. Put that square on that face. Then enumerate load effects. That means write stresses for the effects. So these are the three steps. So once you want to enumerate, just draw that square and work on that.
Just a bit of clarification, in your parentheses there in planner steps, it says pick Z and what?
It's zero, it's zero.
And
It's zero. So you see that when you pull, there's nothing going on in this direction, right? So pick Z in that direction. I can actually spell it out. You were right. Zero is better this way. All right, Dylan, let's enumerate the effects. Look at the force P. It's applied at the centroid, at the center. So what kind of stress do you expect when you pull? Tension. Give me please the equation for that. That's the easiest stress type. When you pull or push,
F over A.
F over A equation, the left side is what is equal to F over A?
Sigma.
Sigma equal to F over A. In what direction is that?
Positive.
Yeah, what direction? In terms of X, Y, or Z?
X.
X. So that's why you said positive, you put outward in the direction of X. You said that pure A. The value is given as 24 kilos, so times 10 to the 3. An area is cross-sectional area, 80 by 120, but median is -3. So 2.5 megapascal. Dylan, do you think it exerts any other stress type? It's applied at the center. Does it bend?
No.
Does it rotate or torsion?
No.
Okay, that's it then. The element is there. It's the easiest element that we could come up with. I mean, we did much harder than this. Dylan, the point. So we want to come up with the stresses on that face that you see on the groove. So really we want to come up with this, sigma x prime, and tau x prime y prime. And guess what? That's the very first example that we did. So if I quickly switch to that example, this is this one. The very first one, we had all the stresses on this fiber, which was 70 degrees from the horizontal axis. We calculated sigma x prime, tau x prime, y prime. So really we have to do these two equations again. So sort of repeat the problem from now on. So sigma x prime So here we found sigma x equals 2.5. Tau xy was 0 on x plane, and y, sigma y equals 0, tau yx is negative of tau xy, also 0. Really only one non-zero value here. And theta is the angle on this. Theta is the angle between x and x prime. So if this is x, which we picked as x prime is this. So really this is, you need this as the theta. So if this is beta, if I draw that in here, this is beta, which is 22 degrees. This is my x prime, and this is x. So I need this theta. So if this is 22, this is 22 as well. So theta is 90 minus 22 degrees, which is 68 degrees. So sigma average is 1 plus sigma x plus sigma y over 2. So 2.5 plus 0 over 2. 0.5 minus 0. Cosine of twice 68 degrees, and tau is 0. That's sigma x prime. Tau x prime y prime. Yes, calculate these and get a point for each.
Sorry, I must have missed it. Why did you cross out the tau?
Because it's 0. You see there's no tangential stress here. So tau is 0 here. Here previously we did have these tangential ones, each one was 40.
Okay.
Guys, again, this is for your advantage. Let's keep trusting each other. Let me give you your values. Confirm these. This is, again, for you guys. Do that and resolve any issues that could occur. My point is not to put anybody on the spot. Rather, to make sure that you all get the most out of this. So if you're confirming, confirm both. Bossy, 2 points. Drew, 2 points. Justin, 2 points. Jacob. Olivia. Reagan. Reagan. Jackson. Audrey. Leo, Nathan, Sterling, Gabe, Pax, Aidan, Kiro, Paul, I'm sorry, was so close I didn't see. Element. Ethan. So again, by knowing the material properties, glue's properties, then you're able to determine whether the glue is safe or not. Two values, sigma U value you would need, and tau U you would need. You practice so much of those. All right, so what did we do here? We're able to come up with the element, what the stress values are on that, and then from here it was really all a calculation that was repeated. This for we want to repeat this for a new problem. But before that, guys, any questions? All right, very good. Let's move on to the next one. Another practical problem. And as you're writing this down, 2 points, yes. Tyler. And Jesus. Josiah, you see Tyler, Hero is in between us, and then you go behind his head and you do like this. I'm not sure he ever loses that hair. No? That's the G?
Only for work term.
So as you're writing this down, give me some applications of this in practice. The component is loaded in two ways. You're pulling on it, you're torquing it.
Like a
Finally.
well, like a gear and a gearbox, like the
Yes.
like the shift force.
The axle of that.
Yeah. Change that and then. Nice.
You would not get any underwood, but go for it.
Propeller.
Propeller.
An airplane.
If there is that, let's say there's a leeway to move in that direction, yes. You see, that is there, torque is there. But propeller,
Well, wouldn't they propel it forward?
but not because it's moving to that direction, right?
Yeah.
Propeller is facing that in that sense, it's just rotating.
Yeah. Okay. Yeah. That's
Yeah.
the force.
Yes, Dave.
Sorry, just to confirm, you're asking for applications?
Applications.
Drive shaft of car?
Drive shaft, yes. Any other application? It could be really easy, yes.
Yeah, like the shaft and your windshield wiper motor.
You see, you're an engineer.
Say again?
You are engineer then,
Appreciate it.
right? Yes, great. Point to you. Any other application?
What's the question? Sorry.
What, I just said it, what's the application?
What?
For the 4th time. What's the application for that? Yes,
The shaft for inside of a doorknob.
doorknob.
Principle.
I was waiting for that. Any other application?
The inside of like an electric screwdriver.
Screwdriver. Now, yes, you're thinking. One at a time, yes.
A drill?
A drill bit, yes. Jesus. Yes, Jake.
Bottle cap.
Bottle cap, yes. Cool.
Forgive me if it's already been said, but steering shaft, you want a direct opinion from the.
Yes, loading is also listed, pushing that. Evan? Done. Corkscrew, yes, Max?
How about a swivel chair? Chair, swivel chair?
Yes, yes, good thinking. Evan watched there before I forget, just 1 second, let me give the one to Max, okay, go for it.
There's a padlock,
What kind of lock is that? Remind me.
like the one that you twist.
Yeah. Had lock,
It's a combination.
EAD.
Oh, combination lock.
Yeah, it's
Combination.
a combination.
Okay, just say I want to always make you confused. Yes, okay.
Drive shaft, differential.
It was mentioned already. If you didn't hear it, I believe you. Didn't hear it? All right. All right, so let's put our coordinate system. So we said that once you see the load, take that as x. Y or z really is symmetric, it doesn't matter, but if you go y this way, z becomes this direction so that you can put the square on this space, which is easy for us to see. If you switch the two, then it becomes underneath and that's hard. Again, torque has symmetric effect. All right, then we have the square. Guys, remind me, who helped me with the sigma x value? It was Dylan. You helped me with that, right? All right, Jesus. Jesus helped me. We have the load here along x. What kind of effect does it have? By this force. What kind of stress this
A
force?
torquing?
On this force. This is torque, this is force.
Mm-hmm.
What kind of stress this force creates?
A pulling force?
What kind of stress?
Say again?
What kind of stress? Like the previous example.
Yeah. I said pull force?
Yeah.
Yeah.
Sigma equals
F over A.
F over A.
Yeah, F
What
over-
direction is that?
In the X direction?
X direction. All right, put that in here. We have that. What's the area of a circle?
2 pi r? Oh, wait.
That's the perimeter.
The area. Oh.
Area.
I times area.
Integrate that, you get
Uh-huh.
the area. 2 pi r that you said. Integrate that.
2 pi r.
Pi,
Pi 4 over d squared?
yes, or pi r squared.
Oh, pi r squared.
So it's 16. So sigma x is 2.5 megapascal. Oh, I'm sorry, it's not this, it's probably the previous one. 32.33. All right, you have that. Jesus, would the force create any other stress?
The force creating any other stress?
Look at the force only. It's applied at the centroid. Does it apply any other stress?
No.
No. That said that, let's move on point to you. Braden, let's look at the torque. The torque, what kind of stress it creates? And we learned it in leg 1.
You want the equation?
Yes, please. So you have torque, what kind of stress do you have?
Shear.
Very good shear stress. Tau equals,
B cube over,
no, that was for bending.
oh, that's for
it has to have T torque in it. Tau equals
P over R.
Is it V over A? No, that's not. it.
rate, yeah, it has to have T in it.
Oh, is it T over J?
T times something over J. You cannot read your own handwriting? T
No.
times something. All right, I think I have to not give you the point so that you fix it for your, Olivia and Justin, I saw first, I think you guys go for it. You give me the tau and you give me the term in the denominator, yes. You give me the equation for tau
Okay, tau is equal to T times R over J.
times R over J. And then you please, Justin, give me the J equation.
I don't have that currently, so I'm gonna pass.
All right, then Gabe,
J is 1/2 pi R naught over minus.
Leo,
J is equal to 1/2 pi R naught to the cube to the fourth.
4. So, Gabe, just look at this geometry. Is it hollow?
It is not
So then the rest that you were saying was not needed.
Yeah. I see the original. I got like 3J equations.
Yeah, I'll give you a point for it. Gabe, Leo, each a point. Now, I don't know whether I give the point to Olivia or not. You don't think so?
I don't know.
Yeah. Because I don't know either what I do, I give the point to everybody. You may get one extra or the same as everybody, just to be fair to everyone. All right, so that means if you make me confused, then you get the extra point. All right, yes, TR over J is the stress coming from torsion, and we know that shear stress is all about these tangential ones. So for one of them, I simply put the tau value, TR over J, and you say J is pi halves R to the fourth. So torque is given as 200, radius is given. I can cancel out one of the R's, but I can leave it there for simplicity. R is 16 milli. So the tau value is 31.08 megapascal. Remember, when there is tau, it has a symmetric effect throughout that circle. So the only effect is that, just the tau. But Braden, I think I have to give a point to you because that was the first time this question was asked for quite some time. And you said for torque, it has only tau, and you did say the shear stress, that was the resulting stress out of that. And you did give T over J at least part of it. I give you a point for that, Braden.
I'll work on my handwriting.
Yeah. No matter how much you do, still I have the worst handwriting. So I get the point there. All right, so now, Kiro, we want to come up with the sign of these four arrows, the arrowhead of these fours. So just look at this torque. Guys, please pay attention. Guys, everybody, look at this torque. And look at this face that is in contact with that torque. Does it get pushed up or down? Up, that's correct. So if we have this up, what is the direction of this? All right, the other two?
The bottom one would go to the left, and one to the left would be going down.
Well done. Cure point. All right, we have that. Then the element again is much simpler than the ones that we have started with. Only 2 elements there. So it says, find the principal stresses. All right, we know that sigma max and sigma min. Sigma max. Jacob, please give me the equation for these 2.
Is that the sigma average plus R? And then sigma average minus R?
Very good. And Justin, please give me the equation for R. So I'm working backward.
Is
With star.
square root of sigma x minus sigma y divided by 2, that whole expression squared, plus tau xy squared.
Confirm this, please. Yes? Is this the one? All right. So sigma average on this one, this is easy. All right, let's calculate these. Point to Justin.
Yes. Thank you.
Again, for the test, I will do that. Start with the equation, plug in values, then figure out the final value. Yes.
Shouldn't sigma min be negative?
It is. Thank you very much. It is. Who else wanted to say that? I saw extra hands. Give it up so that I give you a point. Point to Jacob, Kiro, Drew. All right, thank you.
Oh, that's one.
So Nathan, Josiah, and Paul, the 3 of you, for the 3 criteria that you see here, one for you basically in order, give me whether this system is safe based on calculations that we have and why. So Nathan, based on this alone, would you say this is safe and why? Yes, yes.
I would say, sigma max.
Yes, you're comparing this with sigma max and
It is safe.
so safe. All right, good. Just the next one.
Comparing to sigma max and sigma compression, we don't have any compression forces, so it's safe.
No, look at here, the sigma max, sigma min, and tau max.
Oh, we do have,
Sig-
okay,
Yes. Oh, did you fix this? Did you fix this?
okay. So we-
Initially, I did not have that negative sign there. Maybe we're referring to that. We do have negative
So
sign
it is
here.
not safe.
All right, good. This is less than 18.87, not safe. Yes, Paul?
Comparing tau u to tau max, 35 is over 32, so it's not safe. And
Not
then
safe.
that means that all of it's not safe.
Exactly. So remember, even though the load, the torque was this, we never thought that anything else would contribute to torque, right? But look at the equation. Max torque does get some contribution from sigma x. That's why we have slightly more than the input. All right, any questions on this? All right, so that we have more done for the next class so that we can leave earlier as Cole liked. Let's, I'm going to pick up on from this point now. So let's take a look at this one. Yes, Jay. I thought that you were raising your hand. So more or less the same applications that you guys gave me for the previous one applies to this one. But if you were able to come up with a new one, let me know, I'll give you points. This is from textbook, and I was asked to include this one by professors from machine design course. Apparently you're gonna need this there. Yes, sir.
Was the question applications?
Yes, something that was not mentioned already. Yes, go for it.
It kind of reminds me of those, the valves, to open a valve.
Yes. It was mentioned previous session too. Nathan, go for it.
It reminds me of a pitot tube.
What tube?
A pitot tube on,
What is it?
race cars and stuff, it's a tube to gain,
Oh, to
Yeah.
bring that out?
yeah.
So how do you spell it?
PITOT tube.
Thank you. Nathan, great piece.
It kind of reminds me of those old like style gates, like it'd be like a frame of a gate, like the swinging gates,
Frame of the,
yeah, like a canopy or something.
yeah. We can visualize one. Great. Yes, Jesus.
Conduit?
What that?
Conduit, like the stuff that
Conduit.
we put wires into to pipe out.
A pipe, yes. Conduit. Braden?
I was thinking like one of those can opener, like the food can.
Yeah. And then was someone more. Drew, go for it.
The shape might not be quite exact, but it
Yeah,
kinda
shape
reminds
doesn't
me-
matter.
But it kind of reminds me of an Allen wrench.
Yes. Even the shape is that, right? Some of them are not exactly hex, or circular too.
Which I hate.
Yes, go for it. Justin, you said it, right?
I just have one word.
I would not give you extra point, but go for it.
Oh, I would say a bolt, like a deadbolt on a door.
Yeah. But it was basically a wrench, that was a wrench, yes.
Reminds me of the other type of door handle.
And doorknob was mentioned, right?
Yeah, just reminded me of that one.
And when you say it reminded me of being mentioned too. Yes.
Boomerang.
Boomerang. But, yeah, come on. But the load is like that, it has that effect, not just the shape, it has that effect that you see.
Yeah.
All right, we have about 8 minutes left, so let's see how much of this we could get. So the coordinate system is already put there, but we have to put at the center that H. All right, still X, Y, Z are the same. So the point H is given to us. It's not clear whether it's exactly on that line. It matters if you go slightly up or bottom. Let's go slightly below so that the signs are picked appropriately. Overall, the exact values will be the same. So put that in slightly below that point. So we want to enumerate the facts. Drew, okay, I think it's your turn. This force F, let's enumerate the effects of it. Are you actually loading or pulling or pushing on H if you load it like this? No, then no axial effect, no F over A. All right, well done. And then, are you causing any torsion? Are you twisting it in any way?
Well, it would be causing some form of shear stress moving across the surface.
Very good. And the equation for shear stress? We just did it.
Yeah, right. That is the, that is, sorry for stuttering, that would be the torque times radius of that IC.
All right, very good. You have that. Does it cause, actually, you gave me enough. Let me give you a point. Wasi, does this force create any bending? That's a solid geometry.
Yes.
About which axis? Look at AB, component of it. Does it curl around?
Is that why?
The axis is, this one is Y, this one is X, this one is Z. This component, as you load it like this, bends or curls around each axis. One was torsion, it was talked about.
X.
X, yes, it bends about X. The stress will be in what direction? So you said MC over I, that's bending. You said about X. All right, these two get X. But the stress will be in what direction? We had this problem before. Cantilever, loaded like this, we said stress is? If I give you the 3 axes, this is X, this is Y, this is Z. The load is like this. The stress is what direction? Open question, guys. What's the stress direction in this case? MC over I that you calculate. Yes.
Z?
I mean, one more chance. Then the third one remains. I mean, let me say it. It's always in that longitudinal direction. It's in the direction of elongation or shortening of that member. So really stress is in that direction. In this case, AB is elongating or shortening along Y. So it's along Y in this case. So sigma Y and point H, because I'm pushing on point D, it will be stretched. So I put it positive like this, and sigma Y will be MC over I, MX, IX, and C of point H. Let's come up just with the M and T values, and then that would be it. Was you gave me one response for X, and let me give you the point for that. Evan, moment X. Look at the force. Look at the axis X, Y, Z that is at the centroid at point H. You know the moment is force times arm, right? For bending, what's the arm?
From the force.
Yes. What's the arm value? What's the arm length?
18 centimeters.
The one that causes the component to bend, not to rotate.
10.
10. 150 times 10. All right, so this is 15. All right. And Tyler, help me with the torque value, please.
Oh,
Torque is the same way, force times the arm. Give me the arm of the force that causes the torsion. 18. 27. Tyler, point. All right, I think this is good. We continue this next class. Make sure you finish up your homework, guys.